All right. So uh, last time we learned that for any sorting algorithm, in that we compare the elements of the array or the list that we have to sort, then we show that any sorting algorithm uh, will have the worst case situation is at least n log n, right? So last time we proved it that we cannot have any algorithm that is better than n log n for the worst case situation, right? So that's why we have merge sort, heap sort, and quick sort. Quick sort is for the average case, of course. Uh, they are optimal in the sense that we cannot find any algorithm that is better than those sorting algorithms. Okay, so today we will review uh, a very famous algorithm that is the radix sort, and we will see what kind of complexity the radix sort has. Okay, so let me share with you the radix sort algorithm and some motivation about why radix sort was a big deal back in the 19th century. So, okay. So radix sort was invented by Herman Hollerith, okay, who was at the US Census. Uh, Now, let me give you a motivation about that. Okay, so in 1880, the US Census took almost 10 years to process the data they collected from households around the United States, right? And uh, Herman, at that time, was a lecturer at MIT, and he invented what we call nowadays a radix sort. And using the same, I mean, the idea he has, and also he built a machine for sorting the punch cards. And it helps to reduce the census 10 years after that to just only 6 weeks. So now you know that the previous US census took about 10 years, or every years we have 52 weeks, right? So 10 years means that it's about 520 weeks. And now with the sorting algorithm and the machine he invented, it just took about 1% of that time, right? Little bit more than that. But you can see that the algorithm helped to speed up the process 100 times. And that was the big deal at that moment. Okay. And he went on to build a company, and it became IBM nowadays. And so, you know, the how strong an algorithm can help to speed up some real world applications. Okay. So today we will learn about what is radix sort and what is the complexity. How can we compare radix sort with the new algorithms we have nowadays, like heap sort, merge sort, or quick sort? Okay, uh, which one is better? So now going back to the radix sort, I will simply copy the list we have here. Okay, and we'll explain that or go through step by step to see how it works. Okay, let me copy it first, and then I will stop sharing the document so we can pay attention here on the whiteboard. All right, so we have the list of numbers we want to sort, right? So we have three, so we have radical sort. Here we have 329, and then 457, 657, yeah, 839, and 436, and 720, and finally 355. Okay, so here we have 7 numbers we have to sort, right? 329, 457, and the radical sort here will try to sort the numbers with respect to digits by digits. Okay, starting from the least significant digits and then to the one before that, and then the last significant digit. Okay, so let me stop sharing here so I can explain that. Okay, so now the idea of the radical sort, as I mentioned before, is that we will sort the numbers with respect to the digits, right? From the least significant digit to the most significant digit. So we will try to use bucket. So that's why sometimes we call it the bucket sort as well. Okay, so we will have the bucket for the numbers in each digit. So we know that for any numbers, we have only 10 possibilities, right? So from a bucket 0, 1, and I have to make it a little bit bigger. Okay. So because we have 3 digits here, so we have bucket for 0, bucket for 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so we have 9 buckets for different possibilities of the digits. Okay, so we will start from the least significant digit here. Okay, so we will go from bottom up. So here we have 355. So the number is 5. So we write here 355. Let me choose a different color so we can see it better. Yeah. Okay, so we will choose here 355 and then 720. Okay, 436. 839. 657. 457. Right? And then finally 329. Okay, 329. Okay, so first we scan the list and write or so push it on top of the buckets, right? So starting from 355, push it into the bucket for 5, right? 720, push it. Okay. So if we have n numbers, okay, so the radical sort for n, that said, if we have n number, right, then this step will take n steps, right? Because we simply go here, push it, push it, push it, right? So we have 10 buckets, and then every time when we push it, it takes one step, one step, one step. Okay, so that's it for the first digit. And what we will do is that we will try to copy this number back. Okay, so starting from the bucket 0, we will write down. Yeah. So we will write down 720. And then this bucket has nothing, nothing, nothing. And then here we have 355. Okay. Here we have 436. And then 457, 657, and then 329, and then 839. So you can see that after we copy back, we have the numbers are sorted with respect to the least significant digits, right? So it's the first step. And now we will try to do the same thing, but using the second digits. Okay? So again, we will scan the list from bottom up and then copy, right? So pull out a piece of paper and let me know what is the result after you push in the bucket and then pop them back. So what will you have when you use the second digits? Okay? So I'll give you about 2 minutes. And after that, just type in the message for what you have, right? Okay, so anyone who has a result, what would be the list of numbers after we sort with respect to the second digit? Just type in the list of numbers starting from, the first to the last. Okay, 729. 329. Okay. All right. So let's see what we have. Okay. So it should be 720 first, right? Okay. So 720 first, and then 329, 436. So, okay. So let me write it down here, and then you compare with what you have, right? So first we have uh, for the two. So we should have 720, and then we have 329, okay, and then 436, and then 839, right? And then we have 355, 6, 457, 457, and 657. Okay, so those are the numbers we have. Okay, so let's see. Okay, John, Juban, the first number should be 720. Okay. Oh, I mean, here. Okay. It's number two. So it should be on top of this one, because when you scan from bottom up, this one will be here, right? So let me go step by step so we will see what we have. There is a shortcut that can help me to write down immediately, but let's start following the algorithm. So 839. So we have it here, 839. Keep in mind that we follow the second digit, right? So 329. So here we have 329. And then 657, right? 457, 436. Okay. 355, and then 720. So we will write down here, okay, from the bucket 0 to the bucket 9. 720, 329, right? And then 436, 839, okay, 355, 457, and 657. Okay, so that is what we have. Okay, so that is for the second digit. And again, we scan this one, it takes n steps, right? Every time we push it to the top of the bucket. Okay, so now we will sort this list with respect to the last most significant one. Okay, and you can follow the algorithm by yourself, but let me just follow it here so we can write down the result. Or maybe you can try it one more time, right? 2 minutes, and let me know what you have. So I hope everybody will have a correct answer this time. Okay. So what will be the final result when we sort with respect to the most significant digits? Okay, so who has it? And by the way, Caleb, you had it right last time, okay? Okay, all right, very good. So looks like you did it right this time. So just write it down, right? So we have 329, and then we have 355, and then we have 436, 457, and then 657, 720, and 839. Okay, so that is the final result. So let me check it. 436, 457, 657. Yes, that's correct. Okay, so here is the final uh, sorted list. So you can see that here we just go from the least significant digits, right? Copy down, copy back, right? And then for the second one, copy down, copy back. So what is the complexity? So you can see here in this algorithm for this particular example, we have the best case workstate and the average case. They are both the same, and that is what? Copy down, take big O N, right? Copy back another big O N, right? Okay, so if we have n numbers and a fixed number of digits for all of them, then it's big O N, okay? Where n is the number of numbers that we have to sort, right? Okay, is it correct? It looks like it's controversial, right? Previously, we showed that any sorting algorithm cannot have the worst case situation. So anything better than n log n. N log n would be the, say, smallest number of complexity. So here it looks like we have big O n for this sorting. So someone say that, well, actually, this radix sort never compare between any two numbers in the list, right? And someone say that, well, quicksort, merge sort are comparison-based algorithm. And this algorithm does not compare between any two of the numbers we have to sort. So maybe it's better because of that. Is it right? Maybe, okay. uh, no, it's not. Okay. This algorithm is worse than the quicksort and merge sort. And the fact that we don't compare any two numbers is a minor thing, it's not the main thing. Okay. So here's the main reason. We say that the complexity is based upon the number of numbers we have to sort and also the number of digits, okay, because we have to go through each digit, right? So what will happen if the first number is not 329, but it may be, say, 7, 4, 2, 5, 6, okay? So it means that what will happen if the numbers are big, or some of them are big, like the first one has n digits, right? The second one can have 3, the next one can have one digit. So what will happen in that case? The complexity is big O(n) times k, where k is the number of digits, okay, for all numbers. All right. So that said, if the list of numbers have, instead of a fixed number of digits, it can have, for example, here we have 7, right? Here we can have 49 digits, for example, okay? Or n squared. In that situation, big O, I mean, the complexity of the radix sort will be n cubed instead of n log n like we have for quicksort or merge sort, right? So here, when we analyze the complexity here, we have in mind that we just have only 3 digits. And then we have to go through, each digit here, yeah, 3 times, right? Copy, copy, right? And then go to second one, copy, copy, and then the last one, copy, copy, right? So that said, this one is a good algorithm in the sense that it helps to speed up the US census close to 100 times faster, right? And then, Herman went on to build up a very successful business that is the IBM nowadays, right? But if we analyze the algorithm carefully, then it cannot be better than quicksort and merge sort we have nowadays, especially when we have the numbers are big, right? The number are big, so in that situation, and also they are imbalanced. Like one is very huge, and then the other ones just have few digits, and then in that situation, the algorithm will be worse than, much worse than n log n. Okay, so it's just only one example to show you how we prove the bound for n log n, which is we say that n log n is the optimal sorting algorithm. And at the first look, we may think that radix sort is a linear sort, meaning big O(n), but it's not, right? For the worst case situation like this, then we say that it's much worse than n log n, like we have for quicksort and merge sort. Okay. Any question about this? All right, very good. So the next thing we will learn is about what we call red-black tree. Okay. So did you learn red-black tree before in data structures or in operating system? Now remember that last time when we learned about heap, someone informed me that heap has been used for operating system for scheduling the processes, right? Okay. But nowadays, some new operating system, they do not use heap for, scheduling processes. Did you learn about Linux and its kernel, or just Windows? Oh, okay, very good. Uh, so operating systems are evolving, we know that, right? Because we keep improving the operating system. That's why we have iOS, uh, 16, every 2 years, right? So the latest, actually starting from the kernel 2.6 of the Linux, and they switched to, instead of using the heaps, and they now switch to red black tree. Okay, so there must be some ideas or also some advantages by using red black tree. But first, I will try to give you some motivation about why do we need to have the red black tree, and what are the red black tree anyway. Okay, so first question. Okay, uh, what would be the complexity for using searching on a binary search tree? Okay, let's say if we have a binary search tree like this, 1, 2, 3. Okay. So binary search tree is a data structures, right? In that we use the nodes and the structures of the tree that help us to speed up the searching process. Remember that when you learn about binary search, I use the array, right? So array of numbers. For example, we have 2, 4, 7, 9, 12, 14, 16, 18, right? So binary search on an array means that if we want to search for 8, right? So we jump to the middle, right? Okay, we jump to the middle, right? And then compare. If it's smaller than the value of the middle, then we search for the left, right? So that is the array, in that we have the indexes of elements, so we can know how to jump to the middle, how to jump to the middle of the small array, right? So similarly, when we have a huge amount of data, the advantage, one of the advantages of having the array is that it's fast, right? We allocate the array, and then when we access to the indexes, it will be very fast. But the disadvantages, the array has a few of disadvantages, and one of them is that we need to allocate the consecutive memory for the array. And if the array is big, it becomes a problem, right? So that's why you learn both linked list, or in other words, in this case, we have tree. Yeah, basically it's a linked list, right? So we have the left and then the right pointers, right? Left pointer, right, etc. So the binary search tree is the tree that satisfies a few conditions. Number one is a binary tree. And then the value of everything on the left is smaller than the value at the node we are standing on. And then the value of everything on the right will be bigger than the value at the node we are standing on, right? So if we have a binary search tree, then we can search for any elements very fast by going to the root, which is the middle value on the array, right? And compare. If it's smaller, then we search on the left subtree. Otherwise, we search on the right subtree. If they are the same, we just print out that yes, we found the element, right? So that is the binary search tree. So binary search tree is very similar complexity when we have the binary search on an array, meaning it just takes big O n step, log n step when we search the binary search tree, right, for finding an element. However, sometimes, or the worst case situation is it takes n steps. Okay, why n steps? So here is the motivation for you. So first, the binary search tree is a binary tree that satisfies some order condition, as I mentioned before, right? So now here we have a binary search tree, right? What will happen if I insert a new element into this tree? For example, I want to insert 5. What will happen? What should I do? I guess for the binary search tree, you already learned about that, even in 280, right? CMPS 280. So we already learned about the binary search tree. Okay, so what will happen if I want to insert 5? So we will start from the root, right? Okay. Compare. It's bigger than 2. We go here, right? Then it's bigger than 3. So we know that we will insert it on the right hand side of 3. Right? So that's it. We will insert 5 here, right? Okay. So now, similarly, if we insert 7, 9. So what happened? If we keep inserting elements, the tree becomes imbalanced. So in this situation, you can see that the height is no longer log n, but it becomes n, right? It becomes n. So that said, binary search tree is a good data structure for us to search for the elements in the list, or in other words, on the tree, if the tree is balanced. Like if you have a tree that is balanced, for example, when it's full, right? Like this. Then we know that the height here is log n, right? So in that situation, if we search for an element, then we will go on one branch, and that said, it will have the height of the tree at most in order to search for an element, and that is the big O n, right? Also, when we have a balanced tree like this, inserting a new element will also take, say, big O n, log n step, right? Removing an element will also take us big O log n step. So if the tree is balanced, then we have insertion, searching, removing their own big O log n steps. In other words, it's very fast, right? So the question here is that how can we keep the tree balanced? So when we have a binary search tree, it's very hard to keep the tree balanced. Okay? For example, in this case, if we keep inserting 5, 7, 9, or 15, etc., then we destroy the balancing of the tree. So that's the motivation for having what we call the red-black tree. Okay, so what is a red-black tree? A red-black tree is a binary search tree in that we use two colors, red and black, in order to color the nodes. And we use that to help us to keep the tree balanced. Okay, so let's see. I will give you one example. Okay, let me show you one example here. Okay. So for example, here on the share screen, we have a red-black tree. Okay. So a red-black tree, as you can see here, is a binary search tree. Binary search tree means that the value of everything on the left subtree is smaller than the value at the node we are standing on. For example, if we pay attention to node number 7 with the number 7, everything on the left subtree is smaller than 7, and everything on the right subtree is bigger than the 7, right? And you can also see here that we use two colors, red and black, in order to balance the tree. Okay. So another thing we want to use here is that we also use the what we call the none node. If you pay attention to node with the number 5, you can see that it has two red pseudo children. Yeah. So the red, I mean, two black nodes, they are known value. It means that it has no pointer. Okay, so it has no value and the node has no pointers. In other words, they are the leaf. Okay, so that said, we will try to have some notation here. Yeah. Okay, so let me have this tree again. And I will use one example for inserting, for example, 5. Okay. Or let me have it this way. So let me have one example and then we will try to see how it works. So we will have the following tree. So we have 7, 5, 9, and then 8, 12. And that's it. And we just use the color red here. Okay. So the first thing we see here is that it's a binary search tree first, right? So meaning everything on the left of 7 is smaller than that, everything on the right of 7 is bigger than that. So it's the binary search tree. And then we use the color. You will learn how to color them a little bit later. But right now, I just want to give you one example in that I have 2 red nodes, right? And now we have every node. This one with a number we call an internal node or a real node, right? Every real node will have 2 children. So This one, we have an empty or the null children, right? Null can be something like this. It's just a pointer that's point to an empty node, right? Everyone will point to that, or we just keep an empty or null node here, right? So everything will have a null node. Okay. So from here you can see that every node we have two children, right? Okay. So that is another property of a red-like tree. And the last thing is as follows. Okay. On this tree, if you count the number of red, it can be arbitrary. But if you count the number of black nodes, then every branches will have the same number of black nodes. Yeah. So for example, here, starting from 7, I want to count the number of black nodes on every branches, starting from 7. So keep in mind that when I count the number of black nodes on a branch starting from 7, I will not count the color of 7. Okay. For example, here, this branch will have 2 black nodes. 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay. So this one is a red-like tree. So remember that a red-like tree is a binary search tree. Okay. It has either red node or black nodes. Every branch starting from a node, any node including the root, we have the same black count. Okay? Or if you count starting with this node, how many black nodes you have for the branches starting from 9? 1, 1, 1, 1. Starting from 8, 1, 1. From 12, 1, 1, right? So all branches of the tree starting from any node will have the same black count. And that will help us to have the tree balance. Okay? So you may ask, in this situation, it does not look like it has a balanced tree, right? But later on, we will show that for any red-like tree, the height of the tree will be big O log n. More precisely, big O or 2 times log n, which is also log n, right? It has maybe twice the height in comparison with a full binary tree, but it's just only about 2 times at most, right? So that said, searching, insertion, deletion of a node on the red-like tree will be always big O log n, which is very efficient, right? Okay, so that is about the motivation and also answering the question, what is a red-like tree anyway? Okay, so again, I just mentioned about the criteria or the condition for being a red-like tree. Okay, so you may ask, yeah, having a balanced binary search tree is good, but what can we do with that? Right? So many real-world applications are using the red-like tree nowadays. Okay? So, for example, Linux kernel start to use red-like tree for scheduling of the processes. instead of using hip before. Why? Because if we use red black tree like this, we have a balanced tree. More than that, it uses the memory. We don't have to allocate consequent memory space for a heap, like when we learn about heap sort or building a priority queue using heaps, right? So that's the main reason why the latest kernel of Linux started to use the red black tree instead of using a huge array. Okay, so that is about the motivation. So now, how can we handle the color? So starting with insertion. So when you have a red black tree, we will learn that, okay, I want to insert new elements. I want to remove some elements from an existing red black tree. So what should I do? Okay, so let's see. I will have the following examples. So I will try to insert 11 into this tree first. And then after that, I will have a hands-on exercise to work with you for building up a red black tree from scratch. Okay? So let's say start with 11 first as an illustration for how can we add a new element into a red black tree. So the idea here is that we want to insert 11 into this. How can I insert 11 into this? What should I do first? Remember that a red black tree is a binary search tree, right? So in order to insert 11 into this tree, I have to find a place where I will insert 11, right? So that said, I will start from the root. 11 is bigger than 7, so I will follow the right link, right? 11 is bigger than 9, so I will follow that. 11 is smaller than 12, so I will follow this. This is a known pointer. So that said, I know that is where I will insert 11 in, right? So I will insert 11 in here. When we insert 11, we will create two known pointers because that is a requirement for red black tree that every node will have exactly two pointers. And the first thing I will do is that I will color it red. Okay? So when I insert a new element in, always color the new node red. Now, here is a problem. In a red-black tree, besides the order condition, like it's a binary search tree, right? And we have two colors, red and black. And then on every branch, starting from a node, we have the number of black count are the same, right? So that said, if I don't color this one red, we will have a problem, right? When I insert 11 in, if I don't color it red, then if I look at the root, this branch has 1, 2 black count, but this one has 1, 2, 3, right? They are not the same. So that said, this one is not a red black tree. Okay? So that said, the first thing I will do is to count it, to color it red. Then I resolve the problem with the black cow, meaning here I have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, right? So we are good with the number of black cow, but it has a problem, meaning on a red black tree, you cannot have two red notes in a row. Here I have red and black, that's fine. But here I have red, red. It's not allowed because if we have two red notes in a row, then the height of the tree will no longer be log n, right? So that is the final condition for the red light tree, meaning we cannot have two red notes in a row. Okay, so what can we do? In this situation, we will try to do the following thing. Okay? Assume that previously we have a red light tree. When we insert a node in, right, we will look at how we call this. This one has the parent, right? So when we insert a node in, we will look at the color of the uncle. Okay? So now, if we have 11, the parent is red, and we have two red nodes in a row, we have to correct the situation. Correct that by look at the color of the uncle. If the color of the uncle is also red, then what we will do is that we will try to color them, both the parent and the uncle, black, and color the grandparent to red. And change the color here to black. Okay, what will happen when we do it? If we count the number of black nodes, right, it doesn't change, right? Because these two red nodes have been exchanged with the color of the parent of the, I mean, here is the grandparent of the node we are inserting, right? So here's what we just inserted. Okay, so here we have 1, 2, 1, 2, 1, 2, 1, 2, right? So when we change the color here, we will have to check with the great grandparent to see if it's a red node. If it's not, we are done. And now this one becomes a red light tree, right? Because we never have two red nodes in a row. Okay? So that is what we have when we insert a new node. If the parent is red, look at the uncle. Okay? If they are both red, then change the color and change the color of the grandparent and go up to the root. Okay. By the way, the color of the root can be anything. It doesn't change the black cow if this one is black or red, right? If we simply change the color of the root, doesn't matter because here, if we count the number of black nodes on every branches, we have 1, 2, 1, 2, 1, 2, 1, 2, right? But usually we use the black for the root. It's just a minor thing. In fact, the color of the root can be anything because it doesn't change the black cow of the branches. Okay, so that is the motivation. Okay. Now, what will happen if I insert 6 into this tree? I insert 6, right? 6 is smaller than 7, so I will go to the left. 6 is bigger than 5, so I go here. So this one is a known pointer, so I will insert 6 here, right? And I will add the known pointer to 6 and color it red. Okay. Do I need to do anything? Insert a node, color it red. And now we will see if the new node has a violation of the color property, meaning checking the pattern. The pattern is black, we are fine. Don't need to do anything, right? Why? Because the number of black cows on every branches are still the same. Insert a red node, so the number of black cow on this branch doesn't change, right? It's still 1, 2, 1, 2, right? Okay. So now, when we insert 6, that is what we have. Okay. So we will practice with 2 more. And in that, we have to probably have some additional steps in order to maintain a red-black tree. So here is what I will do. So I will have the following exercise for you. Okay. We will have a hands-on exercise like this. Build a red-black tree by inserting the following elements. We have 41, 38. $31, $12, $19, and $8. Okay, so I will start with the first 3 elements, and we'll ask you to do some hands-on exercise for the rest. Okay. So here we have an empty tree, okay? And then we will start inserting 41, 38, 31, 12 into that empty tree. And we will see what we have. Okay, so I will try to use it here. I think we have time for the first 3 or 4 elements, right? So first, we have an empty tree, right? Now we insert 41. We insert 41, and we have known pointers, right? Remember that when we have the first element to be inserted, we color it red. But as I mentioned before, for the root of the tree, it doesn't matter. So we change the color back to black, right? Okay. Now, insert 38. We would have to insert it on the left of 41, right? So we have 38 here. And we color it red. So we have a red-black tree. Perfect. Okay. All right. So now we insert 31. How can we insert 31? Compare, go to the left, 31 here, right? And we have 2. Now we color this one red. Is it a red like tree? We check, right? First, is it a binary search tree? Yeah, it looks like, right? Second, we have red and black colors, right? The number of black cows on every branch should be the same, 1, 1, 1, 1, right? But we have a violation here that we have 2 red nodes in a row. Okay, we have 2 red nodes in a row. So what will we do? Remember that in the previous example, when we insert a new red node here, and if the parent is red also, we try to find out what is the color of the uncle, right? If the color of the uncle is also red, then we change both color to black and change the color of grandparent to red, right? And go up. Go up meaning we will try to see if the color of the great grandparent is also red. If it's the case, then we have to correct that situation, right? Okay. So here, what is the color of 31's uncle? Black. Yeah, very good. Yeah. John Juban, the uncle is here. It's a known value, but the color is black. Okay. So every node should have either red or black color. Here, even though it's a known node, meaning that it doesn't have the value, but it still has the black color. Okay. Okay. So this one is a red node. I mean, this is a red node, but the uncle is a black color. So we cannot change the color of both of them, right? Because we change the color if both the parent and the uncle are red. But here, the uncle is not red, it's black. So what we will do is that we will try to see. Yeah. Here we have 2 red nodes in a row. We will try to spread the 2 red nodes and 2 branches around the grandparent. Okay? So what we call is the rotation. So if the color of the uncle is black, we will try to rotate around the grandparent. Okay, so how can it work? So we will try to rotate. The idea of rotating that is for spreading the 2 red nodes on 2 sides. So in that case, we will not have 2 red nodes in a row, and we still keep the number of black cows on every branches. Yeah, so we will try to rotate it here. So what does it mean with rotation? Rotation means we will bring the 38 up, right? So we will try to bring the 38 up. And 38 up, then 41 will be plugged on the right of that, right? And then this one will be plugged into the left. This one will become the left of 41. This one will become the right of here, right? And then on this side, we have 31. And here we have the 2, right? And now we have the color of 31 is red. When we rotate, we bring the red to the other side. Okay, this is what we call rotate right. Okay, so here, after we have that rotation, we have how many blackout? One. Okay, and we don't have two red notes in a row like this. Okay, so that is what we do if the uncone is black. We will, next time we will prove that if we keep no two red notes in a row, then the height of the red black tree will be big O log n, right? So what I want you to do is that keep adding these three notes into the tree here. Okay, so sometimes you have to rotate right, sometimes you have to rotate left. If the two notes are here, then you have to rotate left. If the new note here is red, you have to rotate left. Okay, or in this case, the color of the parents and the uncones are both red, change the color, right? Okay, so do the last three by yourself before coming to the class on Thursday. All right. So also next time we will learn about how to remove a node. Okay? After inserting, we will learn how to remove a node as well and maintaining the balance of the tree. All right, any question? Any question? No question. Okay, very good. So next time, actually the lecture notes have been posted. I also posted the pseudocode for insertion, right? Meaning we have three cases. Two, I mean the red parent, red uncone, and then red parent, black uncone, rotate left, rotate right. The pseudocodes are there, so next time I will also go through the pseudocodes with you. Okay, and before I stop, just mention that on this Thursday, we will have a practice for programming contest, right? 5 p.m. after our class on Thursday. Okay, so that's it for today.